Here's another rather intuitive idea. Suppose we have an interval a, b, and here is f of a, f of b. Now notice f of a, f of b are equal, you see. Now, there is no way to draw a continuous graph that between a and, or this point and this point on the graph, f of a, f of b, so that we don't create a maximum or a minimum. We must create a max or a min if we're going to draw that kind of graph. And that's what the next theorem is all about. We can, if we start to go up, from this point, if we start to go up, then we have to come back down to get to this point. If we start to go down, we have to come back up to get to this point. In either event, we're going to create either a maximum or a minimum. And if we go straight across, it's kind of a trivial idea. We have, we have a max or a min for all of the points that are on the graph if it's a constant function. So it's the idea that if we draw it like this, then we're creating a maximum right here. Now, this is called Rolle's theorem. And I have to admit that I'm not sure about how to pronounce the man's name. He was a French mathematician, and it's either Rolle or Rolle. His first name was Miguel. Maybe it's Miguel Rolle. I don't know. But at any rate, I don't think he'll mind how we pronounce his name because he lived in the late 1600s to the early 1700s. And I think he'd be pleased that we even mention his name at this point. But at any rate, the theorem bears his name, and it goes like this. That given f continuous on the interval a to b and differentiable on the closed interval a to b, and f of a is equal to f of b, then we can make a certain conclusion. Now, this idea of the differentiable on the closed interval AB, I'll tell you why that's necessary in just a minute. But under these conditions, we can conclude that there is at least one C on this closed interval. That is, there's one C value that is definitely between A and B, definitely between A and B, such that f prime of C is 0, such that f prime of this C, f prime of C is 0 because the slope of that tangent line is 0. Okay, now the differentiable idea is this. If we didn't have this in here and we tried to make this theorem occur, and we say, okay, we don't care about this, then somebody is going to say, well, I can draw a continuous graph between A and B so that f prime of C is not 0. I can draw it so that f prime of C is undefined, and I can do it like this. You see, and here's the C, and or here's the C, and it turns out that f prime of that C would be undefined. So at any rate, it's the notion that we're differentiable along that open interval. Okay, to see that we meet the requirements, we test for whether or not the theorem holds by doing this. Suppose we're given this function and we're talking about this interval. Now, the test for the validity of the theorem, does this situation fit the requirements of the theorem? That's what we're asking right now, just for practice, to get used to all of the requirements of the theorem. We have to show that f of A is equal to f of B. That is, f of one endpoint is equal to f of the other endpoint. That's the first thing. Then we have to talk about continuity and differentiability. But nonetheless, let's see. We would begin with thinking about f of negative 2. f of negative 2 is negative 2 to the fourth minus 2 times negative 2 squared. And evaluating, we get 8. Then f of 2 means, let's see, replace these x's with 2's, and we have 2 to the fourth minus 2 times 2 squared. 2 to the fourth, 16. 2 squared is 4. Minus 2 times 4 minus 8. 16 minus 8, 8. So f of negative 2 is 8. F of 2 is 8. That's part of the requirement. Now we have, this is a polynomial function, so the function is continuous on the closed interval, and it is differentiable on the open interval. So we meet all of the requirements of the theorem. We can apply the theorem by going out and looking for this f prime being equal to 0, f prime of some point being 0. Let's find the point or the points. We know that there is at least one of them by the theorem. So we can go find them, and we kind of know how this works from the last section. F prime of x is this. This is the derivative of the function. And now factoring and setting equal to 0, we find this factored form. The zeros of the function are the zeros of the factors, so the 0 of this factor would be 0. And to make this factor 0, x would need to be -1, and for this one it would be 1. So not too big a deal here. It's kind of an intuitive proposition. This next idea is rather intriguing. It's called the mean value theorem, and it works like this. Again, we have an interval a to b. And I'm going to put in a couple of points, and I'm going to make it so that f of a is not equal to f of b. I'm going to make it something like this. Now I'm going to draw a continuous graph between this point and this point, between f of a and f of b. And I want you to notice something about no matter how I draw this. I can draw it like this, for example, no problem. And regardless of how I draw that rascal, think about the slope of the line containing these endpoints. The slope of the line containing the endpoints. All right, there's the slope of that line. Now, the claim for the mean value theorem is that there is a c which is between a and b, such that the slope of the tangent line at f of c is going to be exactly this slope. You see, there's a spot where we have exactly that slope, and I'm guessing, but I think it's roughly right here on the graph. So the c value would be about, let me see if I can get this roughly correct. If this is the c going straight up, if that's the point on the graph, then the claim is, you see that there's a spot on the graph that has the same slope as this. Now, there are a couple of ways to interpret this. I'm going to give you a formal definition for the mean value theorem in a minute. But the informal idea is that, you know, slope refers to change. And so we're talking about this slope is sort of the average change in the interval, the average change in the whole interval. And this is the instantaneous change at a point. So we could say then that there must be a point in AB, and that point we're calling C. There must be a point in AB. Now notice closed interval, and open interval, and therefore we're talking about a point which is distinctly between A and B, but not equal to or not the same as A and B. Okay. There is a point in this interval at which the instantaneous rate of change is equal to the average rate of change over that closed interval. So the instantaneous rate of change is equal to the average rate of change. It's a theorem that we're going to use for other purposes in just a little bit. Here's a more formal way of looking at the theorem and kind of defining the theorem. F is continuous on the closed interval A to B and differentiable on the open interval AB. There's a point C in the open interval AB such that f prime of C is equal to the slope of the line containing A and B, is equal to the slope of the line containing A and B. Now algebraically, we can write that down rather easily because we know how to write the slope of a line containing 2 points. F prime of C then is equal to, here's the slope of the line containing A and B. Remember the slope formula, m is equal to y2 minus y1 over x2 minus x1. Well, here's the y2 minus y1, f of b minus f of a over b minus a. So this is nothing but a revised form of our slope formula right here. Let's use the mean value theorem in this problem. Here's our function, and we're talking about the interval from 2 to 6. The graph looks like this along that interval. And to use the mean value theorem now, understand what we need to do. We need to find a c such that f prime of c, the derivative at that point, is equal to the slope of the line containing the endpoints, and here's the slope of the line containing the endpoint. So here's what we need to find in this problem. We can calculate this part of it first and then take the derivative and set these equal to each other. I think that's the best technique for us to follow. So f of b minus f of a over b minus a looks like this. Now the right endpoint was 6 and the left endpoint was at 2. So that's why f of 6 minus f of 2, and then down here 6 minus 2. Now f of 6, we can find f of 6 in a couple of ways. One way is to look at the graph. F of 6 is up here at 2, or we can say replace x with 6. 6 minus 2 is 4. The square root of 4 is 2. So that value turns out to be 2, and in a similar way, f of 2 turns out to be 0. So we have 2 minus 0 in the numerator, 4 in the denominator, or 1/2. So this slope, the slope of the line containing those endpoints, is 1/2. Now let's calculate derivative. The function, it's the square root of x minus 2, or we express it as x minus 2 to the 1/2 power, and the derivative then would be 1/2 times x minus 2 to the negative 1/2 times an understood 1, which is the derivative of the x minus 2. Okay, so we have this, and the negative 1/2 will kick this binomial to the denominator. It'll be x minus 2 to the 1/2 in the denominator, which is the square root of x minus 2, and that's why I've written it this way. Now we'd like to, for f prime of some value, or this derivative to be equal to 1/2. So we set it equal to 1/2 and solve for x. So we set this equal to 1/2. We say 1/2 is equal to this, and now solve for x. Cross multiplying, we get this. Dividing on both sides by 2, we get this. The 2's just go out. Squaring on both sides, we get x minus 2 equals 1, or x equals 3. Now, if x equals 3, that's our c value. So we can come back over here, and at x equals 3, oh, here is f of 3. And it just means then in this problem that the slope of the line containing the two endpoints, I apologize for this not being exactly straight, but is equal to the slope of the tangent line at this point, so it should look parallel to that. All right, so that's the whole idea of applying the mean value theorem. Here's another application of the mean value theorem. Suppose we have an automobile that's traveling, and at some point there is a police car on the side of the road. So the person slows down. And let's say the person slows down to 55 miles an hour at this point on the road, and the car is going this way. Okay, so at this point, the police clock this person at 55 miles an hour. Now, exactly 5 miles down the road, there's another police car. And the person slows down again when that person gets to this other police car, and the car is going 50 miles per hour at this other point. Now, the points are 5 miles away. The two police cars are 5 miles apart. And let's say that the time that it takes for the person to go from the first police car to the second police car is 5 minutes. See, those are the ingredients that we need for this situation. Let's calculate the average rate of speed. You see, now all I'm doing is taking the information from the problem and putting into the distance formula. We don't need fancy calculus to work out this idea. It's distance is rate times time. The distance is 5 miles. The time is 4 minutes. And 4 minutes is 4/60ths, you see, of an hour. So multiplying through by 60, we get 300 is equal to 4r. Dividing on both sides by 4, we find r to be 75 miles per hour. 75 miles per hour now is the average speed. You see, given that distance and time, the average speed is 75 miles per hour. And so presumably the police would stop this person and say, instead of giving you the breath test, we're going to give you the math test. Your average speed here, although you were within the speed limit at the end points of our observations, your average speed was 75 miles an hour. Now, the more calculus way of doing this is to think, okay, let's think of dt. I'm using distance in terms of time, or distance as a function of time. All right. And so d of 0, the distance at 0 time, when this time frame starts here, is no miles. Okay, and the distance after 4 minutes is 5 miles. Now this 4 minutes is 1/15 of an hour. And we're going to stay in this miles per hour kind of arena, so we need miles and hours or parts of hours, and that's why I'm changing the minutes to hours. Okay, so d of 1/15 is 5 miles. And with that information, we can go through and calculate average speed with an f of b minus f of a over b minus a. Now, fitting it with our information, it's d in terms of this time minus d in terms of that time over 1/15 minus 0. d of 1/15 is 5, d of 0 is 0, 5 minus 0 is 0, over 1/15 turns out to be 75 miles per hour. So either way we look at it, somebody's busted.